Hi students, in this session we are going to start a new chapter named Matrix Methods. As you all know, in geometrical optics, our main aim is to find the position and nature of the final image obtained when an object is placed in an optical system. അതായത് ജോമെട്രിക്കൽ ഒപ്റ്റിക്സ് അല്ലെങ്കിൽ റേ ഒപ്റ്റിക്സിലെ പ്രധാന ഫങ്ഷൻ എന്താ വെച്ചാൽ നമുക്ക് ഒരു ഒബ്ജക്റ്റിനെ ഒരു ഒപ്റ്റിക്കൽ സിസ്റ്റം, അതായത് ഒരു സിംഗിൾ റിഫ്രാക്റ്റിംഗ് സർഫസ് അല്ലെങ്കിൽ ഒരു ലെൻസ് അല്ലെങ്കിൽ ഒരു സെറ്റ് ഓഫ് ലെൻസസ് ഒക്കെ തന്നിട്ടുണ്ടെങ്കിൽ അതിൻ്റെ മുന്നിൽ ഒരു ഒബ്ജക്റ്റിനെ വെച്ച് കഴിഞ്ഞാൽ അവിടെ ഉണ്ടാകുന്ന ഫൈനൽ ഇമേജിന്റെ പൊസിഷനും നേച്ചറും മനസ്സിലാക്കുക എന്നതാണ് ജോമെട്രിക്കൽ ഒപ്റ്റിക്സിലെ പ്രധാന ഫങ്ഷൻ. Now, finding out the position and nature of the final image is easy if our system, optical system, consists of only a single refracting surface or it consists of say one or two lenses. ഒന്നോ രണ്ടോ ലെൻസ് മാത്രം ഉൾപ്പെട്ട ഒരു സിസ്റ്റമാണ് നമ്മുടേതെങ്കിൽ അതിൻ്റെ മുന്നിൽ ഒരു ഒബ്ജക്റ്റിനെ വെച്ച് നമുക്ക് കിട്ടാകുന്ന ഫൈനൽ ഇമേജിൻ്റെ പൊസിഷനും നേച്ചറും റേ ഡയഗ്രാം വഴി മനസ്സിലാക്കുക എന്നത് അത്ര പ്രയാസമുള്ള കാര്യമല്ല. On the other hand, if our optical system consists of a number of refracting surfaces or if it involves a number of lenses, say 20 lenses, now what will be the final image when you place an object in front of 20 lenses? What will be the nature and position of the final image formed? If our system is complex, then this process becomes highly tedious. അപ്പോൾ നമ്മുടെ സിസ്റ്റം വളരെ കോംപ്ലിക്കേറ്റഡ് ആണെങ്കിൽ അതിൽ ഒരുപാട് ലെൻസുകളും ഒരുപാട് റിഫ്രാക്റ്റിംഗ് സർഫസസുകളും ഇൻവോൾവ് ആണെങ്കിൽ ഫൈനൽ ഇമേജിൻ്റെ പൊസിഷനും നേച്ചറും റേ ട്രേസ് ചെയ്തുകൊണ്ട് കണ്ടുപിടിക്കുക എന്ന് പറയുന്നത് വളരെ പ്രയാസകരമാണ്. So a new method was introduced by Holbach in 1964, and this method is used to overcome the difficulty in locating the position and nature of the image formed when the optical system contains a number of surfaces. അപ്പോൾ ഒരുപാട് ഒപ്റ്റിക്കൽ സർഫസസ് ഇൻവോൾവ് ആയ സിസ്റ്റത്തിലെ ഫൈനൽ ഇമേജ് പൊസിഷൻ ആൻഡ് നേച്ചർ കണ്ടുപിടിക്കാൻ നമുക്ക് ഈ മെട്രിക്സ് മെത്തേഡ്സ് ഉപയോഗിക്കാം. So before going into what is the matrix method, we can see a ray of light when it passes through any optical system, through a cylindrically symmetric optic system, it undergoes two sets of operations or two things can happen. ഒരു റേ ഓഫ് ലൈറ്റ് ഒരു ഒപ്റ്റിക്കൽ സിസ്റ്റത്തിൽ കൂടെ കടന്നു പോകുമ്പോൾ രണ്ട് കാര്യങ്ങൾ സംഭവിക്കാം. One is that the height of the ray can change while the direction remains the same. So this thing here, see the height of the ray will change. The first line with the arrow, the height of the ray is changing but direction is not changing, and this operation is called translation. The ray has undergone translation. Its height has changed as it passes, but its direction has not changed. And the second operation that the ray can undergo when it comes in contact with an optical system is refraction or the change in direction of the ray. See here the ray was coming like this. It has undergone a change in direction due to refraction. And this can be, now these two operations, that is translation and refraction, can be represented by two sets of matrices or matrix operators. One is the translation matrix and the next one is the refraction matrix. So to fully describe the ray propagation through an optical system, we can make use of two operators. One is the translation operator and the other one is the refraction operator. Now, these two operators are called the refraction matrix and translation matrix respectively. Okay. So, once again, I'll repeat, when a ray passes through an optical system, it can either undergo translation or it can undergo refraction. So, these two operations can be represented by two operators, and here the operators are matrices. So, translation is represented by a translation matrix and refraction is represented by a refraction matrix. And the combination of these two, that is, suppose the ray undergoes both translation, refraction, again translation, refraction and all, then the resultant matrix is a system matrix. Okay, so it if the net operation encompasses both refraction, translation and all, that means the matrix which represents the total change undergone by the ray is called the system matrix. The matrix which can represent or which can bring about the total change undergone by the ray is called the system matrix. Okay, so before going into the details of the translation and refraction matrix operators and their forms, we have to know how a ray is specified in this matrix method. How do we represent a ray in a or a point on a ray in this matrix method? So designation of a ray by a matrix is what we are going to learn next. So we consider an optical system for that, say a lens. So that z-axis is forming its axis of symmetry. That is, the z-axis cuts the lens into two halves. Okay. Now, any ray PQ can be represented by two parameters. This ray PQ or a point on this ray PQ is represented by two parameters. One is the distance of that point from the axis, that is from the axis of symmetry. Here the important axis is, or the defining axis is this axis of symmetry. Here it is the z-axis. So the ray, a point on the ray is specified by two coordinates. One is the distance of the ray from the axis of symmetry and the angle that it makes with the axis of symmetry. Suppose I draw a dotted line here, then you can mark an angle here. That angle is the second coordinate that designates a point on your ray. So a ray is represented by two coordinates. One is the distance of the point on the ray from the axis of symmetry, and the second one is the angle that it makes with the axis. Now, we'll consider it with a specific example. Consider the point P on the ray. See, you can see it here, the point P on the ray. Its distance from the z-axis is, or the axis of symmetry is x or x1. So, first coordinate is x1 and the angle that it makes with the z-axis or axis of symmetry is alpha 1. So, x1 alpha 1 are the coordinates of the light ray. Okay, but normally, instead of specifying the angle alpha 1, the second coordinate used is usually the optical direction cosine. What is meant by direction cosine? Suppose you have the ray here, the ray PQ here. Now we find out what is the angle that the ray makes with the x-axis. And the cosine of the angle that a line makes with the x-axis is called direction cosine. So cos theta is the direction cosine here. Now, what is the optical direction cosine? Like how you find out the optical path. Path is the actual distance. Optical path is given by refractive index times the distance. Similarly, here optical direction cosine is you multiply refractive index with the direction cosine. So, mu into cos theta gives you the optical direction cosine. So, if alpha 1 is the angle made with the z-axis, then we consider the remaining angle that the ray makes with the x-axis, that is theta. Cos theta is the direction cosine, and mu into cos theta will give you the optical direction cosine. So, the two coordinates designating a ray are, it is x1 and something in terms of the optical direction cosine given by lambda 1. Lambda 1 is equal to mu into cos theta, that is our optical direction cosine, but it is represented as mu is equal to, and that is equal to mu into cos of 90 minus alpha. Theta is equal to 90 minus alpha from this figure, so that is equal to mu into sine alpha. So, lambda is equal to mu into sine alpha. That is, I am representing the optical direction cosine in terms of the angle that the light ray makes with the axis of symmetry. Lambda is equal to mu sine alpha. That is the equation for lambda that we are going to use from now on. Also, optical direction cosine expressed in terms of the angle that the light ray makes with the x-axis, lambda equal to mu sine alpha. So, at P, now the coordinates of the light ray are x1, lambda 1. x1, the distance of the light ray from the x-axis at that point, and lambda 1 is the optical direction cosine represented in terms of the angle that the light ray makes with the x-axis. So, at any point on the ray can be specified by x comma lambda, and this I represent by a column matrix x lambda, what I've written in the box. So, any array or any point on a ray or a ray vector can be specified or represented by a column matrix x lambda. Now, suppose x1 lambda 1 represents a point on the incident ray and x2 lambda 2 is a point on the refracted ray. Suppose there is an incident ray and it has undergone refraction. Okay, so how will you represent it in matrix method? So x1 lambda 1 is a point on your incident ray. x2 lambda 2 is a point on your refracted ray. Now the ray has undergone refraction. Now how will you represent it using a refraction matrix operator? So we say that a refraction matrix will act on your ray vector, incident ray vector, and you get the final ray vector, that is the refracted ray. So, this is how the matrix method is followed. We say that the refraction matrix operator will act on your incident ray vector and you get the final ray vector. Okay, so since rays are represented by 2 by 1 matrices, 2 into 1, 2 by 1, 2 rows and 1 column, your final answer is a 2 by 1 matrix. Your incident ray is also represented by a 2 by 1 matrix. So, according to the matrix multiplication rule, your refraction matrix must be a 2 by 2 matrix. It must be a 2 by 2 matrix. Similarly, for translation also, suppose there is a point on the incident ray and the ray has undergone translation. Imagine that the ray has undergone translation and the point on the translated ray is represented by x2 lambda 2. So, x2 lambda 2 represents a point on the translated ray. Then x1 lambda 1, it is its initial point, x2 lambda to the final point. Then the translation matrix operator ABCD will act on the initial point and you will get the final position x2 lambda 2. So this is how matrix method is followed. Now what you have to do next is we have to find out the specific representation of the translation matrix and refraction matrix. What is the form of the translation matrix? What is the form of the refraction matrix? Which we'll continue in the next class. So I hope all these things are clear to you. For complex optical systems, we follow to find out the nature and position of the final image. We use a method called matrix method. Complex optical systemത്തിലെ final imageഉം അതിന്റെ നേച്ചറും പൊസിഷനും കണ്ടെത്താൻ നമ്മൾ മെട്രിക്സ് മെത്തേഡ്സ് ഉപയോഗിക്കുന്നു. ഒരു ഒപ്റ്റിക്കൽ സിസ്റ്റത്തിന്റെ മുകളിൽ ഒരു റേ വന്ന് പതിച്ചാൽ രണ്ട് കാര്യങ്ങൾ സംഭവിക്കാം. ഒന്നുകിൽ ആ റേക്ക് ഒരു ട്രാൻസ്ലേഷൻ സംഭവിക്കാം, അല്ലെങ്കിൽ റിഫ്രാക്ഷൻ സംഭവിക്കാം. ഈ രണ്ട് ഓപ്പറേഷൻസിനെയും രണ്ട് ഓപ്പറേറ്റേഴ്സ് വഴി നമ്മൾ റെപ്രസെന്റ് ചെയ്യുന്നു. ഇവിടെ ഉപയോഗിക്കുന്ന ഓപ്പറേറ്റേഴ്സ് ഒരു ട്രാൻസ്ലേഷൻ മെട്രിക്സും ഒരു റിഫ്രാക്ഷൻ മെട്രിക്സുമാണ്. ഓക്കെ, അപ്പോൾ ഈ ട്രാൻസ്ലേഷൻ മെട്രിക്സ് നമ്മുടെ ഇൻസിഡന്റ് അല്ലെങ്കിൽ ഇനിഷ്യൽ റേയുടെ ഡിസിഗ്നേഷൻ റേ വെക്ടറിന്റെ മുകളിൽ ആക്ട് ചെയ്താൽ നമ്മുടെ ആൻസർ ഒരു ട്രാൻസ്ലേറ്റഡ് റേ ആയി കിട്ടും. അതേപോലെ റിഫ്രാക്റ്റഡ് മെട്രിക്സ് അല്ലെങ്കിൽ റിഫ്രാക്ഷൻ മെട്രിക്സ് ഒരു ഇൻസിഡന്റ് റേയുടെ മുകളിൽ ആക്ട് ചെയ്താൽ നമുക്ക് റിഫ്രാക്റ്റഡ് റേയുടെ മുകളിലത്തെ ഒരു പോയിന്റ് കിട്ടും. ഇങ്ങനെയാണ് ദ മെത്തേഡ് ഓഫ് മെട്രിക്സ് മെത്തേഡ് എന്ന് പറയുന്ന മെത്തേഡ് വർക്ക് ചെയ്യുന്നത് ഈ രീതിയിലാണ്. സോ ഐ ഹോപ്പ് this class is clear to all of you. Thank you.